Hello everyone, welcome back to my channel. My name is Rakshit Subramanya and today I am going to be presenting on the topic Undecidability, a language that is not recursively enumerable. This comes under our subject known as TOC, which is Theory of Computations. So let's move on now. So first let's have an introduction on what is this undecidability. So undecidability usually refers to an algorithm which cannot provide a constructive answer, that is a step-by-step process answer. So here you can see here undecidability refers to problems for which no algorithm can be constructed to provide a solution. So that one, it doesn't give you a constructed answer, meaning you don't get an algorithm for this kinds of problems. So these problems often arise in the context of a formal languages and automata theory. As I said, this is from theory of computation, so it comes under automata. These problems are usually seen in automata theory and formal languages, which is also part of this subject. As you can see here, you find these kinds of problems. So understanding undecidability is crucial for grasping the limitations of a computational system. So you need to know the limit of your computational systems. We'll have multiple types of computational systems such as uh, the finite automata, push down automata, Turing machines, and many computational systems. So we need to be able to know the limitations of each computational system. So now let's see the first one, which is your recursively enumerable languages. So usually recursively enumerable languages are those for which a Turing machine can give a definitive answer, or like, how do you say, they take a step-by-step process, that after one step they go to another step, and that's how they go on to give you a definitive answer. So here you can see, as it's mentioned here, recursively enumerable languages are those for which a Turing machine can enumerate a valid string. So it goes a step-by-step process. So every recursively enumerable language can be reorganized by a Turing machine, but not necessarily decided. These languages can be infinite and do not require that the Turing machine halts on all inputs. So what it says that the languages here can be infinitely long, or they cannot be definitive. That is what it's mentioned over there, and it also means that your Turing, as I said, your Turing machine gives a definitive answer. It also says that your Turing machine doesn't need to give a definitive answer. So here is a diagram for that, so you'll understand how a Turing machine works, where S is your input, which is we are going to get from a recursively enumerable language, and it either accepts it or rejects it. So moving on, now let's see about decidable versus undecidable languages. So these decidable languages and it is a language based on which your Turing machines are built. Now, like most of your machines, such as accepting a value, not accepting a value. So this is how they are built. But there is the use of undecidable languages also. Now let's see. As I mentioned before, here you can see decidable languages is the one where Turing machines can always provide a yes or a no. In contrast, undecidable languages have no such Turing machine that can always halt with a definitive answer. As you read before, in the recursively enumerable one, the Turing machine does not need to halt. It can halt, but it doesn't mean that it has to halt. Here what it's telling in decidable and undecidable languages, in decidable it says that it will halt at either yes or a no, and in undecidable language it's telling it is never, it doesn't mean, or then like there is no language which can help the Turing machine to stop at one definite answer, that is either a yes or a no. It won't happen like that. So this distinction is very fundamental in understanding the limitations of your computational system, that is your Turing machine or any other machine that we'll be using. Now here are some of the examples of undecidable problems, mainly being the halting problem. So as we read it, the halting problem is a classic example of an undecidable problem. The problem, so what is this problem? So it's like the problem asks whether a given Turing machine will halt at a given input based on the given, like whatever input you're giving, and if that input has no algorithm which can solve it, that like you have an algorithm which can solve every aspect of that problem. So that is what it says. So as you can read it, the problem asks whether a given Turing machine will halt on a given input and no algorithm can solve it for all cases. There are more examples that include your post correspondence problems and the problem of determining whether a context free grammar generates a specific string or not. In theory of computations, in engineering, you will mostly be dealing with the problem of determining whether a context free grammar generates a specific string or not, while the other one is which you go through when you go into your deeper studies. Now, whether languages that are not recursively enabled. No, so we read about languages which are recursively enumerable. Now we are going to see languages which are not recursively enumerable. So some languages cannot even be enumerated by a given Turing machine. This makes them non-recursively enumerable, or like, how do you say, undecidable languages, as we mentioned before. They're not enumerable. So as an example for this language, you get a set of all Turing machines that do not halt at one definitive answer, and these languages are like not only undecidable, they also come, like, you see, as we met, they come into this category of non-recursively enumerable languages. So here you can see in the diagram, as we mentioned on the recursively enumerable languages before, you can see here the recursive languages first, and then there's recursively enumerable languages, and they also come as non-recursively enumerable. So what it says is that these languages are not only undecidable but also fall outside the class of recursively enumerable languages. So we talked about recursively enumerable at the first. So this, as you can see in the diagram here, the recursively enumerable and the recursive languages both do not lie within this. So it is a totally different type of language. So the characteristics of a non-recursively enumerable languages. Non-recursively enumerable languages cannot be recognized by a Turing machine. That is the standard. They are often associated with problems that are too complex to be solved by your computational systems, or they're too ambiguous for computing. And understanding these languages requires uh, like going into a very deep study of a given certain logic and expertise in that area. So as I mentioned before, the ambiguous means the number of faults, how many faults are there in that given characteristics that you're going to use, in the given input that you're going to use for that machine. So now let's see the implications of undecidability. The existence of undecidable languages limits what can be achieved with algorithms and computational programs. It challenges the it challenges the belief that all problems can be solved through computation. This has profound implications for fields such as computer science or mathematics or philosophy or many different branches that you see under this. Now, the role of the goals incompleteness theorems. So the Gödel's incompleteness theorem illustrates that in a consistent formal system, there are statements that can be proven true or false. In case I read the name wrong over here, I'm really sorry. It is very hard for me to pronounce these names. So these theorems can these statements. I mean, sorry. This theorem, that the Gödel's incompleteness theorem, is mainly illustrates that in any consistent formal system, there is a statement that cannot be proven either true or false. So these theorems provide a theoretical foundation for understanding the undecidability. They show that not all mathematical truths can be derived from a finite set of axioms. Okay, now coming to connections to computability theory. That is, undecidability is a core concept within computability theory, which that studies about what can be computed and what cannot be computed about a given statement or an input by a Turing machine or a computational system. So the study of undecidable languages leads to a deeper understanding of computational limits of a given computable system. So researchers continue to explore the implications of these findings in both theoretical and practical contexts. Now coming to practical applications and limitations. Although undecidability poses challenges, it also helps the us know the boundaries of a computational function, and which can help us to like create or innovate to make sure that we are able to surpass these boundaries. So understanding these limitations can guide the development of an algorithm and the programming language. So awareness of an undecidable problem is essential for a software engineer and a computer scientist, as they are the ones who are going to be mostly working on these kinds of systems. And finally, coming to the conclusion. Okay, now, so what all we learned up till now, that is, undecidability highlights the limitations of computation and the complexity of certain languages. That is one. Two, what we learned is that the study of languages that are not recursively enumerable continues to inspire research and debate. And lastly, we learned that recognizing the boundaries, or that is the limitations of your given function, helps us in our understanding to it basically enriches our understanding for pushing across the boundaries both in theoretical and practical aspects. So these are the three main aspects that we learned today from undecidability. So I hope you understood something. Thank you.